All right, so in this module, we're going to talk about what we call the electroneutrality condition, and this will allow us to start to solve these equations that we've just written down for all the different oxygen regions. And so what the electroneutrality condition is it's at, we're talking about at equilibrium, so at equilibrium, at any state, we have to have a condition where the concentrations of the various species, and those are defect species, have to simultaneously satisfy all of these mass action expressions. With one further condition. And this is known as the electroneutrality condition. So the important thing here is that not only this electroneutrality condition that I'm going to show in a second, but also that we have to simultaneously, at equilibrium, simultaneously satisfy all of the mass action expressions. So that's pretty powerful because it means that all of those are valid. And so we don't just have to pick a mass action expression looking at low PO2, right? It still applies in all regions. So that's kind of an interesting thing as we look at that. But let's get to the electroneutrality condition, which basically states that there's a sum of positive charges, and this is per volume, and that's equal to the sum of negative charges per volume, right? So it's a fairly straightforward condition, right? We're just looking at a sum of charges. So all the positive and all the negatives, right? Because we can't have a net charge like we've talked about before. So the difference here, though, is that we tend to write our things in terms of concentrations. So if we want to write that electroneutrality condition in terms of concentration, then instead of the sum of the charges per volume, what we get is the sum of concentration of each species multiplied by its effective charge per defect. And that equals the same for the opposite charge. All right, so let's just think about that for a second. So if we're writing it in terms of concentrations, then it's going to be a sum of the concentrations of each species, and then it's going to multiply by the effective charge per defect. And then that's all equal to the same for the opposite charge, right? So this is a different way than what we're seeing here in terms of just summing up all the charges, because we're talking about concentrations. So what I want you to do is we're going to go back to the slides for a second, and I'm going to put up a question that'll be on the quiz, and I want you to answer, see if you can answer that, and then come back and we'll work it. And it's related to trying to write this electroneutrality condition for our MO oxide system. All right, so like I said, what I want you to do is try to answer this question before we discuss it. and see what you get, and then come back and we'll work this together. So I want you to see if you can write that electroneutrality condition we just discussed on the paper for our system, but in terms of concentration. So see if you can write that out and then come back and we will work this together. All right, so now that you've had a chance to look at this, let's go ahead and write this out as a class. So for the electroneutrality condition for this MO oxide, and again, I wanted this in terms of concentration. So what we're going to first do is just kind of list out all the positive and negative species that we might have. So, that entails going back to kind of look at some of the other stuff that we had, right? So let's go ahead and kind of take a look at what we had. So for the low PO2, we had oxygen vacancies, we had electrons. For high, we had metal vacancies and holes. And then for the intermediate, we had the vacancies again, so those are just repeats. And then we had these again, right? So basically, we only had 4 species total, right? We had all the vacancies and then electronic defects as well. So let's write those. So, for the positive, we had oxygen vacancies and we had holes, right? For the negative side, we had metal vacancies and we had electrons, right? So those are going to be our species, and now we need to write that in terms of concentrations. So we're going to start with the positives. So we write them in concentration. So P is for holes, right? P-type conductor. And then remember, we're multiplying that by the effective charge. So the effective charge for an electron hole is +1. And so we just have to multiply this by +1. So basically we don't have to do anything. And then we also sum that with the oxygen vacancies and multiply by the effective charge. And here it's a +2. So we do have to multiply it by 2. And so again, those were all the positive charges we could speak of. And so that's going to be equal to the sum of the negatives. And we'll do the same thing. Concentration site fraction of electrons, so N, and times the charge, so 1. And then the same thing with metal vacancies, and effective charge is -2, so we multiply that by 2, right? So it's quite simple, but it may not make intuitive sense because we're dealing with concentrations here. So, and also you might pay attention to the square brackets. This is going to probably appear a little bit differently than it does in the book. So I'm putting the square brackets here so that to keep everything consistent. So you might notice that they just use N and P, but I'm using the square brackets here. So at this point, we have this condition. Sorry about the focus. We have this condition along with the sets of equations that we had for the mass action expressions. And this will allow us to solve these equations in order to determine the concentrations of these vacancies or of these different defects as a function of PO2. So that's what we're going to do. But in the next module, we're going to try to make it a little easier for us by talking about what we call Brouwer approximations.